Alright, so we're going to go over the natural logarithmic function. This is section 6.2 star from the textbook, the Stewart Calculus textbook. And if you want to just kind of sign in by just leaving your name in the comment section, just so I know who's following, that'll be fine. Alright, now we've gone over a little bit of this before spring break started, which was a long time ago now. So I don't feel like it's a bad idea to kind of go through some of this again. We're defining the logarithm, the natural log function, ln x, as the area under the curve of 1 over x. So in other words, we're saying, oops. All right, so we're saying, we're saying the integral of 1 to x of 1 over t dt. And remember, the t is just like a dummy variable to kind of help us understand what's going on. Well, what I'm saying is the t is just a substitute, so that once you do the integral, you end up with a function of x, right? Your variable, your true variable, is here. And the idea is you have this curve of 1 over x, which looks like something like this. And starting at the point 1, I want to measure the area underneath up until a given stopping point, which is x. All right, and that area is what we mean by ln x. Okay, that is the area under the curve. All right, now an interesting thing about this. Oh, I lost my spot. The nice thing about doing this live is that everyone can see how bad I am at this. An interesting thing about the logarithm is that if I take the derivative of it, well, I mean, think about the fundamental theorem of calculus. What's the derivative of the integral? Well, fundamental theorem of calculus says it's just, well, the function, right? So the derivative of ln x is 1 over x. Okay, and that's kind of the big takeaway of the logarithm. And what's nice is in the past we've had where we can integrate 1 over. We've had in the past where we can integrate 1 over x to some power, but we haven't been able to integrate 1 over x. So what I mean is in the past we've said something like this. Sorry, in the past we've said something like this, 1 over x squared dx. Well, I know what that is because that's x to the negative 2 power. So I just raise the power by 1 and divide by that power, so I end up with negative x to the negative 1 plus c. But the integral of 1 over x we haven't had until now. Now I know that that is ln x plus c, and that is the indefinite integral of that. Okay, now the logarithm has a few interesting properties attached to it, which I want to address. Okay, so here are a few laws. The first one is that if you have a product, we can turn a product into an addition statement. Like that, okay? Secondly, if I have a division statement, I can turn it into subtraction. And thirdly, if I have x to some power, ln x to the r, I can take out that power and turn it into multiplication. So that's going to be r ln x. Now, how do we justify these? Well, it's actually easier to justify them if we use the algebraic definition of the logarithm. because what we say is that a log is actually an exponent. And so if you're adding two expressions, for example, a to the m times a to the n, or multiplying, I mean, a to the m times a to the n, you get a to the m plus n. And so if you're thinking about this being pulling out the exponent of two multiplied expressions, you're just getting the sum of their exponents. Okay, it's an exponent property thing. All right, now as an example of this, of kind of what you can do with this, and this is just for practicing, we can look at, well, let's just try practicing our logarithmic properties here. This is example 2 in the text. Okay, I want to express, or actually, we should say expand. I want to expand this expression, ln x squared plus 5 to the 4th power sine x all over x cubed plus 1. Okay. Now I'm just using my properties of logs to pull this apart as much as we can. And I think we might have actually done this example in class, but it's worth going over again. All right, so what I can do here is I'm just applying these three laws, 1, 2, and 3, to pull it out as much as I can. So I notice I have division. So that's the first thing I would say is like, look, I can expand this out. And I should be careful here. What I want is ln of x squared plus 5 to the 4th power sine x, right, that's my numerator, minus ln of the denominator, x cubed plus 1. From there, I can break up multiplication and I can take out exponents. Now what you can't do is you cannot break up an x cubed plus 1. There is no ln of a plus b equals something expression. We have to leave the x cubed plus 1 by itself. Okay, but what I can do is break this up as ln x squared plus 5 to the 4th plus ln sine x minus ln x cubed plus 1. And then finally, I can take out the power, and I end up with this expression, which is, in my mind, a simplified version of what we started with. It's a simplified version to me because because it's almost like a linear expression. It's have plus and minus. Okay, so logarithms get manipulated in funny ways, but they are extremely useful, and we'll see them in a variety of contexts. Okay, and again, if you have any questions, just leave them in the comment section. I'd be glad to go over that. Now, another thing is, if we looked at the graph of a logarithm, so if I looked at the graph, I'm looking at y equals ln x. All right, now remember what we're talking about is the area under the curve going from 1 up to x, right? Going back to the original, we're looking at this expression. You're going from 1 to x, area under the curve. So if I'm going something but before 1, going out this way, I'm going to actually get a negative area because I'm starting at 1 and I'm moving backwards. So before 1, this thing should be negative, and it is. All right, so here's what it looks like. Ln x hits 1, or hits 0 at x equals 1. Before that, it's going to be negative, and it's actually going to have an asymptote. And then from there, it kind of tapers out, and it looks like it may be asymptotic. Is it, though? I mean, does it have a horizontal asymptote? Well, actually, it doesn't. Okay, so here's a couple things we could say. If I'm going out to infinity, if I take the limit as x goes infinity of ln x, does it go to something finite? It does not. It goes out to positive infinity. All right, so going out this way, I just keep going up, even though it's going up kind of slow. Now, on the other side, if I approach 0, and I can only approach 0 going from the right of ln x, so I'm going this way towards 0, what happens? I'm dropping down to negative infinity. So I do have a vertical asymptote there at 0. Okay, good. And again, I hope this is all making sense to you. All right, now from this, we're going to introduce a new definition. So here's what I'm interested in. What about when I hit a height of 1? Since it goes to infinity, since my limit goes to infinity, eventually I am going to hit 1. And what is that number here? That's what I'm interested in. Okay, so at what point do I hit 1? And we could play around with this by just taking the area under the curve, maybe doing some sort of Riemann sum idea. But we're just going to make a definition. E is the number such that if I take ln of E, I get 1. So that number that I was looking for, this question mark here, is the number E. All right, now we could try to find this with a graphing calculator or other ways, but what you'll find is that E is approximately 2.718, 2818, so on, so on. We usually just say 2.718. All right, now E is irrational, so we can write it like this. E is not in the rational numbers, so E is irrational. So like pi, its decimal expansion never stops, just keeps going on and on. But the funny thing is that E shows up in a variety of contexts. So if we're going to talk about logarithm, we also need to talk about E, right? So we're going to keep up with both of these things. But don't forget that E is a number, all right? And what number is it? It's the number 2.718, but where does it come from? It's a number such that ln of that number hits 1, all right? So it's the value that makes this graph get up to 1. Okay, now getting back to ln, we said that the derivative of ln x, was 1 over x. So because of that, what if I had this? The derivative of ln u du, or the derivative of ln u. Okay, what's it going to be? Well, you're going to have to use chain rule here. U being what? U being something other than just x, possibly. It could be a function of x. Well, that's going to be 1 over u times the derivative of u with respect to x. Okay, and now this is going to provide a lot of interesting opportunities for us to integrate and to differentiate. For example, example 5, here I want to take the derivative of y equals ln x cubed plus 1. I want to take the derivative of ln x cubed plus 1. Okay, so here I have a function, x cubed plus 1. I have to remember now, this is chain rule when I'm taking the derivative of it. The derivative of ln u is 1 over u times its derivative. Okay, so the derivative of y, we'll say y prime, is going to be, well, u is this x cubed plus 1. So the derivative of ln x cubed plus 1 is 1 over x cubed plus 1 times its derivative, which is 3x squared. So here we end up with 3x squared over x cubed plus 1. All right, I hope that makes sense. Let me know if it doesn't. All right, Courtney, you asked, what does the Q mean? Yeah, right here. Sorry if I didn't specify this. This is the set of rational numbers. All right, so we have a few kind of sets designated in mathematics. The double stroke R means the reals. The double stroke Q is the quotients or the rationals. Double stroke z is the integers. And double stroke n is the natural numbers. That's good to know. And we don't use it in this class, but the double stroke c is the complex numbers. All right, so those are kind of our big sets of numbers that we keep up with. So yeah, what I'm saying here, E is not in the set of rationals, therefore E is irrational. Okay, now going back to example 5, I hope it makes sense. We can look at another one just to make sure we feel good about it. So example 6 from the text, we want to find the derivative of ln sine x. The derivative of ln sine x. All right, so now, again, we are making u to be what? Sine x. So when I take the derivative, it's got to be 1 over u du, right? So here, the derivative of ln sine x then is going to be 1 over u, so it's 1 over sine x, times its derivative. The derivative of sine x is cosine x. So here I end up with cosine x over sine x. And we could call it a day there, but we remember from trigonometry that cosine over sine is actually the same thing as cotangent x. Wow, that was kind of surprising. The derivative of ln sine x is cotangent x. So if you think back, we never really learned the integral of cotangent x. But now we know it. The integral of cotangent x would be ln sine x plus c, right? Okay, good. Let's see. Let's look at one more of this, and then we'll move on to a new topic. Example 8. I want to take the derivative of ln x plus 1 over the square root of x plus 2. Okay, so if I do that, I'm going to have to do some sort of quotient rule or something like that. All right, now there's actually 2 ways to do this. So one is we could just try using chain rule and quotient rule, which we'll do. The other way we could do this is by using properties of logarithms. And so let's go and do both, all right? So method 1, and I'm going to show you why. Well, here's one thing. So in some of your classes, like if you're taking a physical chemistry class, you may be using tables of integrals to get solutions, or you'll notice that your calculus text has a table of integrals as well. And sometimes you may do an integral, you think you got it right, you check the table, and the table's got a different form than what you had. That doesn't necessarily mean you got it wrong. It could just mean that they are using different algebraic techniques to calculate it. Okay, so let me show you what I mean by that. Here's a good example of this. So method 1, I'm just going to use product rule and quotient rule. I'm sorry, chain rule and quotient rule. So first I'm just going to say, all right, my u is all of this. That's my u. So when I take the derivative, I'll just call it y prime. And let me pick a different color. I like jumping around the colors. Y prime, we say 1 over u. Well, 1 over u would be the reciprocal, right? So I start off with the reciprocal, square root of x plus 2 over x plus 1 times the derivative of u. And the derivative of u here, we're going to have to use quotient rule. It's been a long time. Remember quotient rule? Low d high minus high d low over low squared. So here that's going to be, again, low times the derivative of the top, d high, that's 1, minus high times the derivative of the bottom, which would be, what is that, 1/2 times x plus 2 to the negative 1/2 power, times the derivative of what's inside, which would be 1, all over low squared, the square root of x squared plus 1. I'm sorry, the square root, let me say that again. The square root of x plus 2 quantity squared is simply x plus 2. So looks kind of gross, right? Actually, it's not terrible because remember, let's think for a moment. What is this x plus 2 to the negative 1/2? That is 1 over square root of x plus 2, right? So if I distribute this across, it actually cleans up pretty nicely. When I multiply square root of x plus 2 times the square root of x plus 2, what do I get? I get x plus 2. When I multiply square root of x plus 2 across all of this stuff, well, when I multiply it times 1 over this 1 over square root of x plus 2, that just becomes 1, right? So I end up with there 1/2 times x plus 1 all over x plus 1 times x plus 2. Okay, now what I can do to get rid of that 1/2 in the numerator is multiply the numerator and the denominator by 2. So I'm going to multiply 2 across everything, and when I do that, I end up with 2 times x plus 2 minus x plus 1 all over 2 times the denominator. And from there, I can combine, get my common terms together and bring it together. Let's see, we get up with 2x minus x is x, and 4 minus 1 gives me a 3. Did I miss something? No, that's right. Okay. What did I say? Plus 3 all over 2 times x plus 1 times x plus 2. And there is my solution. Now I paused for a moment because in the book it's actually square root of x minus 2, not x plus 2. But whatever, we did it correct. We did it correctly. Okay, now there's the algebra is what makes this tricky, not really the calculus, but you did have to know quotient rule. If you had forgotten quotient and product rule, you need to make sure you go back and understand them, okay? Go back and review them. All right, now for method 2, what I'm going to do first before I take my derivative is I'm going to apply properties and logarithms. So for method 2, let's pull this thing apart first. So the derivative of ln x plus 1 over the square root of x plus 2, that's the same thing as taking the derivative of ln x plus 1 minus ln the square root of x plus 2, right? Because the property logarithm says that if you have division, you can turn that into a subtraction statement. So now I'm going to take two derivatives, but they're much simpler than the derivatives I just dealt with. And I end up with 1 over u for the first one. That's going to be 1 over x plus 1 times the derivative of x plus 1, which is 1. And then minus 1 over square root of x plus 2 times the derivative of square root of x plus 2, which is 1/2, right? Drop the power by 1. X plus 2 is a negative 1/2. Okay, now notice here, again, remember, x plus 2 to the negative 1/2 really means 1 over square root of x plus 2. Right? So when I simplify this, I end up with x plus 1 minus, let's take out the 1/2, 1 over square root of x plus 2 times 1 over square root of x plus 2 becomes what? 1 over x plus 2. And there it is. There's my solution. And believe it or not, these two things are saying the same thing. If you had gotten a common denominator and brought them together, you would get the same thing. Okay, but algebraically they look very different at the moment. Any questions on this so far? Hopefully this is making sense. It is safe to say that in the first one we're just trying to machine this out using all our derivative rules. We feel really good with our derivative rules, so we're using quotient rule. With method 2, we are applying a little bit of smart algebra ahead of taking the derivative, and so actually the algebra and the calculus was much easier in method 2 for us because we weren't just trying to dive in head first, right? So sometimes if you do a little bit of massaging before you take the derivatives, it makes it a lot easier on you. All right, good. Okay, now let's switch gears a little bit. Let's look at the more analytical geometry side of this. And we're going to try to graph one of these logarithmic functions. And then what I want to do is I'm going to use Wolfram Cloud to kind of verify our work, see how we did. So this is example 9. We want to discuss, and by discuss we mean graph, y equals ln 4 minus x squared by graphing. And we're using the strategy that you learned in Cal 1 in section 3.5. So there's several things we need to look at. We need to look at the domain, the intercepts. Can we find vertical asymptotes? Those kind of things. Where we really start looking at it is, or where the calculus comes into play, is when we start looking for min and max and concavity shifts. And remember, you have to look at the first and second derivatives for those. Okay. All right. So first of all, domain. What is the domain of this thing? Now, you can only plug in. I mean, let's go back and look at the graph of a logarithm. We didn't really discuss what the domain of the logarithm is. I guess we could here, though. I mean, look at the graph. It's only defined for x greater than 0. Okay, so the domain of ln x is 0 to infinity, right? You cannot have something negative plugged into the logarithmic function. All right, so with that in mind, when I'm looking at ln 4 minus x squared, I need 4 minus x squared to be greater than 0. Okay, which means then that I need 4 to be greater than x squared, which means if I take the square root of both sides, that means that, well, we have to be a little bit careful. When I'm taking the square root, I have to include plus or minus. Okay, so this means that x has to be less than 2 and greater than negative 2, right? Because if you think, if I pick something smaller than negative 2, let's say like negative 5, and squared it, then negative 5 squared is bigger than 4, right? So that's a problem. So the technical way to say this would be that we need the absolute value of x to be less than 2. And so that the absolute value then drops to be this. So saying it as one statement, x is between negative 2 and 2, or in interval notation, our domain just goes from negative 2 to 2. Okay? All right, now for what do we want to do next? So just I'm following the text here. If we look at for a y-intercept, how do you find a y-intercept? You just let x be 0. So if x is 0, we get ln 4 minus 0. So my y-intercept is at ln 4. All right, and if I want to know the x-intercepts, I let y be 0. And I got to figure out how does this happen. So when does logarithm, the ln of what gives me 0. So if you remember back from the graph, let's see, when do I cross the x-axis? At 1. So when my input into the logarithmic function equals 1, ln of that equals 0. So this question, 0 equals ln 4 minus x squared, is really the same equation as 4 minus x squared equals 1. Okay? And so that means from there, algebraically, we end up with x squared equals 3. Or if I add the x squared over and subtract 1, so x equals plus or minus square root of 3. There are my two x-intercepts. Okay. Now, I think from this, we can kind of start getting an idea of what our graph's going to look like, and I guess I'll put it right here. I know that I have a y-intercept at ln 4, and at negative root 3 and positive root 3, I have my intercepts, and I know that if I go out to negative 2 and 2, somewhere out here, my whole graph has got to fit in between negative 2 and 2. That's what I know so far. Okay? Now, continuing on, in the text, part C, we're looking for symmetry, like is this an even or an odd function? And if you want to, we can go ahead and say, look, if I plug in negative x into this logarithm, and here by f of x, I'm letting f of x equal this ln 4 minus x squared, even though we never said that. If I plug that in, notice that if I plug in negative x quantity squared, that's the same thing as ln 4 minus x squared, which means I get the same thing as f of x. So if I plug in the negative value, I get the exact same thing as the positive value. That means that this is an even function, and an even function is symmetrical about the y-axis. So whatever happens on this side is also going to happen identically on that side. Well, when I say identically, a mirror image along the y-axis. Okay, so that's another thing we know about this graph. So actually, if we only figure out the positive part, we'll know exactly what's happening with the negative part. All right, so kind of running out of room over here. Let me come here for part D. We want to find vertical asymptotes. All right, and so what I know is going on, well, my domain endpoints are negative 2 and 2. Okay, so if I can figure out what's happening as x goes to negative 2 of this function, well, I know that, think about what's inside this logarithm, the 4 minus x squared. So what happens, let's see, what happens to 4 minus x squared as I get close to negative 2? Well, I'm getting close to 0, right? It's a polynomial, I can just plug it in because it's a continuous function. And the same is true if I plug in positive 2 into this limit. Okay, so on both sides, as I'm going to positive 2 and negative 2, my what's inside the logarithm is getting closer to 0. Okay, so that means that this is the same as going to 0 from the right of ln x, which we know is negative infinity. We have vertical asymptotes here at negative 2 and 2. Okay, so that's what this translates to. Vertical asymptotes at x equals plus or minus 2. All right, now from there, we're going to start doing some calculus to kind of figure out increase and decrease and concavity. And it may feel like it's been a while since you've looked at that stuff. That's completely fine, okay? So for E part, we're going to find increase and decrease intervals. And if you remember, what you need to do that is to look at the derivative. So let's find the derivative. First of all, what's f prime of x? Again, f is what? F is this ln of 4 minus x squared. So when I take its derivative, that's going to be 1 over u, which is 1 over 4 minus x squared, times its derivative, the derivative of u, I mean, which would be negative 2x. So my derivative now is negative 2x over 4 minus x squared. Okay, now from there we have to find what we call the critical points. And the critical points are where the derivative equals 0 or are undefined. So one we find from letting negative 2x equal 0, which means x equals 0. That's a critical point, so that could be a min or a max. The other part is where the derivative equals 0, which we know is going to be plus or minus 2. And we know that that's not going to be our min or max because these are my asymptotes, right? Those are my vertical asymptotes. So the only possible min or max is the 0. Now, how do I figure out which one? Well, we could either use the first or second derivative test. I'm going to use the first derivative test. And the way you do that is we're going to set up an interval here. So here's negative 2, here's 0, here's 2. All I need to do is figure out a test point to plug in to my derivative to see if I get positive or negative. Let's plug in the test points negative 1 and 1 because I think this will be easy to do. And I'm plugging them into the derivative f prime. So if I plug in negative 1 into f prime here, let's see, I get negative 2 times negative 1 over 4 minus negative 1 squared. That's going to be, let's see, negative 2 times negative 1 is positive, and the denominator 4 minus 1 is positive. So my derivative is positive between negative 2 and 0. It hits 0 at 1. I mean, it hits 0 at 0, right? That was my critical point. And then let's figure out what it's going to do at 1. If I plug in 1, I get negative 2 times 1 over 4 minus 1 squared. Negative 2 times 1 is negative over a positive value. That's going to be negative. All right, so how does that translate to the derivative? If you remember, the derivative measures the rate of change or the slope at a given point, right? So here I have a positive rate of change, which means from negative 2 to 0, I'm going up. From 0 to 2, I'm going down. All right, so that tells me then I am increasing from negative 2 to 0, and I'm decreasing from 0 to 2. I hope that makes sense. All right, so let's see if we can connect that here. I know at this point I'm going up, and that point I'm going down, and I got to hit right at ln 4 and these 2 points. And these are asymptotes. So I got a pretty good feeling about what this is going to look like already. And the only thing is, why don't we try to figure out an inflection point? Okay, and actually the first derivative test is part F in this. So now let's go on to part G. Part G, we're going to look for inflection points. And so from that, we need to look at the second derivative. All right, so we're taking the derivative of the derivative. So we're taking the derivative of this negative 2x 4 minus x squared. We're going to have to use quotient rule to do that. So the quotient rule says low times the derivative of the top, which is negative 2, minus the top times the derivative of the denominator. What's the derivative of 4 minus x squared at negative 2x? All over 4 minus x squared quantity squared. Okay, you do some algebra on this, you should end up with, let's see, negative 8 minus 2x squared all over 4 minus x squared squared. Now from there, what are my critical points? My potentials for imply that negative 8 equals 2x squared, or real asymptotes again, plus or minus 2. Those are my vertical asymptotes. So concavity, increasing, so something like that. But we could go back and test. Look at my second derivative. So let's plug in 0 just to make it easy. If I plug in 0 into my second derivative, I get my derivative is always negative, which means it's going to be, that's just my, let's take a plot. All right, so I'm going to go to Wolfram Cloud here. Start a new log. All right, so I'm going to have fx, my function. Okay, my backspace key is not working. Good. I hope that makes sense. That was really odd. I couldn't back up, but see how integration, as we had written that much. Great. I lost my video signal. Is everyone still there? A little more careful. I accidentally unplugged my monitor, so everything messed up on me. Okay, now switching to integration. So now we want to look at the absolute value of x plus c. Now why the absolute value? Because in the ln where ln of x, I get f of x is ln of x for x is greater than 0, and ln of x is negative x for less than 0. Well, what happens then is that when I take the derivative, all right, I get 1 over x for x greater than 0, and I'm doing a piecewise derivative here, and I get, okay, now the reason in general, I include the absolute value. Out of that is, again, if I integrate 1 over x dx, I integrate x over be x squared plus 1. Integral now becomes 1 over u, the absolute value of u plus c, or in this case, ln of, oh, and I left out one thing, right? The derivative of x squared is du. 1/2 du equals x dx. Sorry, I got a little, and since x squared plus 1 is always, all right? Okay, now, e ln x over x dx. Ooh, this is a tricky one here. Okay, ln x dx. Ln x over x dx. And this is one that kind of shows up commonly, so I think it's good to look at this one. The trick is, what is my value for u when I'm doing a u substitution? So the x in the denominator is kind of a trick, because that is the derivative. What I want u to be is ln x, because what's the derivative of ln x? 1 over x dx. So now I end up with the integral of, let's say, x equals 1, x equals e, u du, right? Another way of writing this is ln x times 1 over x, and the 1 over x dx, right? The 1 over x dx is my du, and the u equals ln x is my function. So if I want to convert my limits to u's, I can do that. Let's see. If I let, here's x and u. If x is 1, then what is u? u is ln 1. Ln 1 is 0. And if x is e, u is ln e. And what's ln e? Well, remember we defined ln e to be 1. Sorry. All right, so here we're ready now to integrate because we have 0 to 1 u du, which is a pretty easy one. That's going to be 1/2 u squared going from 0 to 1. So that's going to be 1/2 1 minus 0, which gives me the value 1/2. And there it is. All right, it appears my camera has frozen. I think that's because of just all this stuff that's been going on when I accidentally pulled out the cable. So I apologize for that. If you have any questions, let me know. I'll still try to follow along. All right. So let's see. We want to do a couple more. I want to show you 2 more examples. They're both very useful. The first one, example 13, I want to know the integral of tan x dx. And that seems very unrelated to what we're doing. But if you remember earlier, we did the derivative of a tangent value, of a trig value, a ln of a trig value, and ended up with cotangent. Maybe we can do something similar. And that is the idea. What I'm going to say here is tangent is actually the same as sine x over cosine x dx. Okay, so if I let u be cosine, not sine, let's let it be cosine, and the derivative of cosine is what? Negative sine, so negative sine dx. I almost have that, right? I have negative 1 over u du, right? The u is cosine x, the du is negative sine x. So when I integrate that, that's going to be negative ln absolute value of u plus c. And so negative ln of cosine x plus c is my integral for tangent. And there's one more thing we could do. Because remember we had a property of exponents that said the negative can be pulled in as an exponent. So this is ln of cosine x to the negative 1 power, and I don't mean cosine inverse, I mean to the negative 1 power, which is the reciprocal of cosine is secant. So this is the logarithm of secant plus c, and that is how we typically write the integral of tangent. And so that's one we need to file away. The integral of tangent dx is ln secant x plus c. That is incredible that we could figure that out using logarithms, right? Right, it is very cool. Okay, I hope that makes sense. All right, now I'm going to show you one more. Example 14 from the book. And this is called logarithmic differentiation. And we want to do something like this. We want to differentiate, or take the derivative of y equals x to the 3/4 power square root of x squared plus 1 over 3x plus 2 to the 5th power. Okay, now that looks, we could use all of our derivative rules, I think, and be okay here, but that looks pretty challenging. So what we're going to do is something like this. I'm going to take the ln of everything. x to the 3/4 square root of x squared plus 1 over 3x plus 2 to the 5th power. I'm going to take the derivative like that. I mean, not the derivative, I'm going to take the ln like that, okay? And so we're going to do some like implicit differentiation on this. Instead of just trying to apply power rule and chain rule and product rule and quotient rule and all this stuff together, watch what I can do. Because of my properties of logarithms, I can actually say ln y then is, let's see if this makes sense, 3/4 ln x plus 1/2 ln x squared plus 1 minus 5 ln 3x plus 2. How did I get all that? Remember, the divides turns into the subtraction. The exponent I can pull out front. That's how I got that. For the numerator, the multiplication turns into addition. And then the 3/4 becomes a power, and the square root, which is the 1/2 power, becomes a coefficient as well. I can pull out powers as multiplication, right? And now what I'm going to do is an implicit differentiation. So remember, when I do that, I'm treating y as some sort of function of x. So here when I take the derivative of y, or the derivative of ln y actually, that's going to be 1 over y times dy. So I'll say dy dx equals, now the derivatives of all these others are pretty simple. The derivative of 3/4 ln x is 3/4 times 1 over x. The derivative of 1/2 ln x squared plus 1 is going to be 1/2 1 over x squared plus 1, right? Times its derivative, which is 2x. And then the derivative of 5 ln 3x plus 2 is going to be minus 5 times 1 over 3x plus 2 times its derivative, which is 3. Okay, so cleaning this up, 1 over y, well actually, let's just say it this way. dy over dx equals y times 3/4 times 1 over x plus, notice the 2's cancel out here. So I have just 1 over x squared plus 1. Oh, and I have an x in the numerator, don't I? So I have x over x squared plus 1. And then I have minus 15 over 3x plus 2. So there's my dy dx. Now the only thing I need to mention is that y was actually what in the beginning was this big thing. So here I'm going to rewrite that x to the 3/4 power times the square root of x squared plus 1 over 3x plus 2 to the 5th power. All that times 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. And that is a pretty clever trick, right? So that is a nasty derivative, but can you imagine if at the beginning we had to come in here and do product rule and quotient rule with a lot of chain rule going on, and then trying to simplify that algebraically? That would have been a nightmare. So the easier way to do this then is, again, to take ln of both sides. And when I do that, I can use my properties of logarithms to pull this apart as a simpler expression. Once I do that, I do implicit differentiation. Ln y, its derivative is 1 over y times the derivative of y, which is dy dx. And then the derivatives of each of these are pretty simple. 1 over u du is how we're doing it. And then all I have to do is multiply both sides of the equation by y. So I move the y over, and then that's how I get my derivative. That's pretty cool. That'll allow me to take some funny derivatives. For example, we could do something like this. Find dy dx, where y equals, oh, I don't know, how about x to the sine x power? We could do that one. Actually, let's do that one real quick. I think that'd be pretty simple. So y equals sine x to the sine x power. I'm going to let ln y equal ln x sine x. Okay, so that'll allow me then, for properties of logarithms, to pull out the sine x. And now I can take the derivative of both sides. So that's going to be 1 over y dy dx equals, I am going to have to use product rule here. Not too bad though. First times the derivative of the second plus the second times the derivative of the first. And now multiply both sides by y. And y was x to the sine x power. So I have x to the sine x power times sine x over x plus ln x times cosine x. And there is the derivative of x to the sine x power. All right, that's the derivative, or the rate of change at any given moment of this funny function. All right, I hope this is all making sense. I'm sorry for the technical issues. I will practice this. I don't know why my camera froze. I'm sure it had something to do with me unplugging the monitor. If you have questions on anything, I'd be glad to help. I have the assignments on Canvas. I'm going to put these notes on Canvas. And here they all are if you want to look at them. And if you have any questions, please let me know. If you don't feel like this is a good delivery method, let me know through email or some way. I'll be glad to help. I just want you guys to get through this as easily as possible. Just let me know how I can help. It was good seeing you guys, and we'll pick it up on Thursday. Take care.